L'Hopital's rule is a rule that we can evaluate pretty much any limit with. All the stuff that we haven't been able to do with, we can now do. So that word is pronounced L'Hopital, a French mathematician. I doubt you're going to hear from him after this. I've heard it pronounced L'Hopital. If you just call him La Hospital, you know, I don't care how you pronounce it, as long as you know how to use his rule. So it refers to stuff like this. There's no algebraic way to mess with that thing that's inside the limit. So if you look at it, the natural log of 1 is 0. You all knew that. And then 1 minus 1 is 0. So this limit is going to 0 over 0. And we've seen that with almost every limit we've ever looked at that goes to 0 over 0. It's just that before, we always had a way to mess with it until we could, you know, actually just evaluate it directly. But there's no algebra move for evaluating, for simplifying natural log of x over x minus 1. There's a name for this. This is called an indeterminate form of type 0 over 0. We've seen that a lot. We know 0 over 0 is indeterminate. Doesn't mean that this limit doesn't exist. Doesn't mean that it does. Just we don't have a way of figuring it out yet. Another example that we'll be able to do very soon is if you just look at the same exact function, ln of x over x minus 1. And now we want to look at the limit as x goes to infinity. So this is the same as me asking you for the horizontal asymptote of this function. Does it have a horizontal asymptote? So as x becomes large, natural log of x also becomes very large. It increases forever. And then x minus 1 also becomes very large. It's like infinity minus 1. So that doesn't mean that it doesn't converge. That doesn't mean that it does converge. With rational functions, we had ways of telling where the horizontal asymptotes would be, but we don't have any such way with this. So that's where Mr. L'Hopital and his rule come in. The word for this is again, indeterminate form of type infinity over infinity. So just to distinguish between the two things. They're both indeterminate, which means that might be a limit, might not. It's just now we have names for them. So here's the setup. F and g are two functions that are differentiable. And then we have to specify that right at the point we're talking about, if x is going to a, we're going to have to specify that g prime of a isn't 0, just because if it were, we would be dividing by 0. So anytime we deal with quotients in math, really, we always have to be like, as long as this other thing isn't 0. So what it's going to be is f is the numerator and g is the denominator. So think about it as f over g. So we have two cases. Either the limit of f of x is 0 and the limit of g of x is 0. That would be like the first kind of indeterminate form, 0 over 0. Or the limit of both of them is infinity, plus or minus infinity. And actually one can be one and one can be the other, and that's still a type infinity over infinity indeterminate form. So we have to have one of these two cases. If one of them's 0 and one of them's infinity, a whole different set of rules apply. And if one of them's 0 and one of them's 1 or whatever, you actually don't need L'Hopital's rule for that. You could have already figured out the limit without it. So this is for the kind of stuff we see that's either 0 over 0 or they both go to infinity. So here's what you can do. The limit as x goes to a of f over g equals the limit as x goes to a of f prime over g prime. So all the limits we're going to see in this section are of the form something over something. Generally, if they're not, then we don't need any special trick to evaluate them. They don't do the 0 over 0 thing. We just have to be really careful when you're using it. So that's the rule. Write it down. Notice that you're taking the derivative of the top and you're taking the derivative of the bottom, but you're not doing the quotient rule. That's not the quotient rule, right? So the derivative of f over g is g times f prime minus f times g prime all over g squared, right? That's the quotient rule. This is not that. So you're not finding the derivative of the function. It's easier than that. You're just looking at the numerator and differentiating that, looking at the denominator, differentiating that as two completely separate things. And then what L'Hopital's rule is, you're guaranteed that if you can evaluate that limit, they're the same. And a lot of functions get simpler once you differentiate them. So you'll see, oftentimes in one move, L'Hopital's rule just lets you evaluate the limit right away by just plugging in. Okay, so just to be really clear, because I see people do this, this is not the quotient rule. Don't use the quotient rule here. I'm not asking what the derivative of f over g is. I'm asking you to find a limit, which involves using this rule properly. And to prove L'Hopital's rule is way beyond the scope of this class. You're just kind of going to have to take my word for it, because if I showed you the proof, you wouldn't get anything out of it. So let's do that first limit. The limit as x approaches 1 of natural log of x over x minus 1. That's an indeterminate form of type 0 over 0. We don't have any tricks here, but what L'Hopital is saying is that you can do the derivative of the top and do the derivative of the bottom. So do that. You get that, 1 over x over 1. The over 1 doesn't do anything. So it's just the limit as x approaches 1 of 1 over x, which right away is just 1 over 1. You can just punch that in. And the limit's 1. So the way to check these would just be, I guess, to graph ln of x over x minus 1 on your calculator. And then just notice there would be a hole at x equals 1, but it would be right at the 0.11. If you looked at a table or something, that would be pretty obvious. Here's that other example. This is the one where, okay, the numerator blows up to infinity and the denominator blows up to the infinity, but that doesn't really mean anything. It doesn't mean the limit doesn't exist. It might not, but do the same thing. So it's the same function inside there, so it's the same rule. Right, there's the derivatives, it's the same. But now if you just look at it, okay, again, the over 1 doesn't do anything. The limit as x goes to infinity of 1 over x, that's just a classic 0, right? If you look at 1 over x, as x becomes large, 1 over x goes to 0. So we had a rule for that, like a theorem for that a long while ago, but you don't have to cite that or anything. Just if it's the limit, if it's 1 over x or 1 over x squared or whatever, as x goes to infinity, that thing goes to 0. So this function does have a horizontal asymptote, and it has it right at the x-axis, right at y equals 0. And again, if you were to graph it, you would see that. Okay, the limit of 3 to the x over x to the 3. And it's pretty obvious when you look at this. As x gets big, 3 to the x obviously goes to infinity pretty fast. And x cubed also goes to infinity pretty fast. So this is indeterminate, and it's the infinity over infinity. It doesn't really matter which type it is. If you know you're supposed to use L'Hopital's rule, just do the derivative of the top and do the derivative of the bottom. Don't even wait for me. You know you're going to have to do that. You should already be doing it. So we just have to make sure we can use it. It has to be one of those two types. And since this is this section, chances are we're going to be able to use it. Okay, so do it. Derivative of 3 to the x is ln of 3 times 3 to the x. And then that's over 3x squared. So every time, so stop and look at where you're at. Natural log of 3 is just a constant. It's like 1.1. So it doesn't really affect anything. We still have a 3 to the x in the numerator. So that's still going to infinity. And now we have 3x squared in the denominator. Well, 3 infinity squared is still infinity, so that's also still going to infinity. So it didn't work, right? We still have this indeterminate form. We still can't evaluate it. But just think about it. We have an indeterminate form. What's the run rule we have for dealing with this? L'Hopital's rule. So you can just do it again. There's nothing stopping you from using L'Hopital's rule twice. If I'm saying that the limit of that first thing equals the limit of that second thing, well, if you just do the derivative again, then that's got to be the same limit. So you may have to use L'Hopital's rule. 3, 4, 5 times before you get to something that can be evaluated. And just be smart about it. Think about, if we keep taking derivatives of 3 to the x, we're just still going to get a 3 to the x in there. But if we keep taking derivatives of the denominator, think about it, what it's going to be in a couple derivatives. The derivative of 3x squared is 6x. The derivative of 6x is just 6. So with powers of x, if you keep taking derivatives of them, eventually you just have a constant. Do it again. In the numerator, all you get is another factor of natural log of 3, which is just more constant stuff. It doesn't really affect the limit. We could bring it outside if we felt like it. So we still have 3 to the x up there, and now we have 6x in the denominator. So 6x is still going to infinity, right? 6 times infinity is infinity, and obviously the numerator is too. So, but we know we're smarter than that, and we're unfazed, and we say, oh look, if I do it one more time, the denominator doesn't go away, but it just becomes a constant. Right, so we get another natural log of 3 in the numerator, it's just a byproduct of what we're doing, and then finally the denominator is just 6. And here's where you stop. If you tried to do it again, that wouldn't be right, because this is no longer an indeterminate form. The numerator goes to infinity, the denominator just sits there, so everything in there except for the 3 to the x is a constant, and it doesn't matter what those constants are. 3 to the x is still going to go to infinity, 3 to the infinity. So, right, if you use L'Hopital's rule again, you would actually get 0 in the denominator, which obviously is no good, but really don't use it because you can't. This is not indeterminate. It only works on indeterminate forms, and you don't need it because you can just look at it. You don't even really have to justify it. Just say, okay, this thing diverges to infinity, so that's it. If you said this limit just does not exist, I would also consider that a right answer, right? We're just specifying that it goes to infinity. Think about, okay, so next we'll do 3 to the x over x to the 100. I'm just kidding, we won't do that because you would technically have to take the derivative 100 times. But if I did, if I asked you to think about like 3 to the x over x to the 100, okay, if we take the derivative of x to the 100 times, eventually it is just going to be a constant. What is that constant? That constant is 100 factorial, which is an astronomically big number. It's like a space big number. But it actually doesn't matter because it eventually would get down to a constant and that 3 to the x would still be there. So it doesn't matter what that power of x was. So when you talk about things going to infinity, it's kind of like a race. Which one gets bigger faster? And what does that make it do? If the denominator gets really big, it shrinks the whole thing to 0. So all that I'm saying is in a race between an exponential function and a power, like x to a power, the exponential function is always going to win. It actually doesn't matter what the power is, and it really actually doesn't matter what the base of the exponential is as long as it's more than 1. The exponential will always beat it, and the whole thing will just blow up to infinity if that's in the numerator. Limit as x approaches 0 of tangent of x minus x over x cubed. This one's a little trickier. Sometimes it's not just a matter of using L'Hopital's rule, 2-3 times. We have to think and do algebra. So the tangent of 0 is 0. You all knew that. So the numerator is 0 minus 0, and the denominator is 0. So this is indeterminate, and therefore we can use our new rule. So do it once. Now it's the limit of secant squared of x minus 1 over 3x squared. Just looking at the top and the bottom separately. However, secant of 0 is 1. Why? Because cosine of 0 is 1, and that's just 1 over 1. So your calculator could tell you that. So that's still 1 minus 1 over 0. So it's still indeterminate. It's still 0 over 0. We know that's fine. We don't let that stop us, right? So just do it again, right? We don't, I mean, you might be able to think of something clever, but we don't really have any other algebra moves at this point except to start splitting stuff off. So it's indeterminate. Just try using L'Hopital's rule one more time. The derivative of secant squared is 2 times secant times tangent. That 1 just went away. So that's the nice thing about doing the derivative a couple times. If you started with an x, it's always just going to be, okay, then it's just a constant, and then it's just 0. So we did get rid of a term. However, we still have a bunch of terms, and the tangent of 0 is 0, so that makes the numerator 0, and then the denominator is obviously also 0. So it's still indeterminate. So I just cleaned it up a little bit, simplified the 2 and the 6, and then combined the secant. So still indeterminate, still 0 over 0. However, think about taking the derivative of that numerator. You'd have to use the product rule and the chain rule. It wouldn't make your life any easier, right? I mean, it might work, but it wouldn't. The point of this is that certain functions, once you start doing higher derivatives, just either go away or simplify, but this isn't gonna. It's actually just gonna keep getting more complicated. So we gotta be smarter. So what we're gonna do is we're gonna like separate the parts that aren't a problem. So the problem is the tangent of x over 3x, right? Tangent of x over x is 0 over 0 here. The 3 isn't a problem either. The secant squared isn't the problem. Secant of 0 is 1. So we're just going to use essentially the product rule for limits to split this apart into a couple different things and just look at them all separately. All right, so we take the 1/3 out front because there's no reason not to. It would work either way. And then we just split up the limit as x goes to 0 of secant squared and the limit as x goes to 0 of tangent of x over x. That tangent of x over x thing is still 0 over 0, but the limit of secant squared is just secant of 0, which is perfectly fine. Secant of 0 is 1, not 0. So that first limit equals 1, and I guess I skipped ahead a step here. So it really just goes away. And all we're left with is 1/3 times the limit of tangent of x over x. And now you get the idea that if we do L'Hopital's rule one more time, look what the denominator will be. It'll just be 1, right? And the numerator will just be secant squared. And that's nice and simple, and we can just evaluate that directly. Okay, and again, secant of 0 is 1. So now don't use L'Hopital's rule again because you can't. It's no longer indeterminate. So it's just secant of 0, which is 1 over 1, and that whole limit in there is just 1, and all that's left is the 1/3. So you probably wouldn't have guessed that, but if you graph that original function and look on a table, you should see that it's 0. It seems to be going right through 0.333 repeating, right? So that would just verify it would have a hole there, but it should look right. Okay, so these can take a little bit of strategy, and there might have been a different way to do what we just did. There might have been a better way. I don't know. But don't just kind of blindly charge ahead and just keep doing it over and over again and plugging in numbers, because that wouldn't have really worked here. Last one, the limit as x approaches 0 of x squared times natural log of x. We've actually seen this function before when we talked about maxes and mins not that long ago. The natural log of 0 is undefined. There is no natural log of 0. So that's why you can't just plug this in. If you were to look at the graph of this function, it would be extremely obvious what this limit is. There's like nothing else it could be. But that's not proof. So we're gonna prove that that's what it is. But we have a problem here because this, not only is this not indeterminate, it's not a quotient at all. It's a product. It doesn't look anything like the stuff we've been doing. Okay, so we can't evaluate the limit, but we can't really use L'Hopital's rule either because it doesn't look right. So in general, with products and sums and differences, there's always going to be a way to get it to look like f over g. And in this case, it's pretty simple. We're basically going to rewrite x squared as 1 over 1 over x squared. So we rewrite it in this goofy way that seems more complicated, where we just say, okay, x to the 2 is the same as 1 over x to the negative 2. That's just how exponents work. So now we can take that thing inside the limit and rewrite it as 1 over x to the negative 2 times ln of x. The expression we have now looks more complicated than the thing we started with, but now we can do what we want to do with it, which is the only real move we have for these, which is to use L'Hopital's rule. So it's not obvious, but as x goes to 0, natural log of x actually goes to negative infinity. And as x goes to 0, x to the negative 2 goes to positive infinity. So both those functions have vertical asymptotes at 0, which means that's type infinity over infinity. We haven't really seen that, but if they both hit asymptotes there, then it's like infinity over negative infinity, which still qualifies. So all that is to say, just go for it. Do the derivative of the top and the bottom separately. That we're not really sure what we're looking at there, but let's clean it up. Because if we could just plug 0 into this thing, we'd be done. And not only that, if we could evaluate this thing directly, then L'Hopital's rule wouldn't be necessary or even appropriate. So just switch that. I just switched it back to like regular exponent notation. That denominator is negative 2 over x cubed. This is a compound fraction. It's ugly, but we know how to clean that up. Just instead of dividing two fractions, just multiply by the reciprocal. That's an old rule, right? So that's my favorite way of cleaning up compound fractions, is just remembering that, oh, that means 1 over x divided by negative 2 over x cubed. So that's just 1 over x times negative x cubed over 2. And then that simplifies a bit because we can cancel one of those x's. That's the limit as x goes to 0 of negative x squared over 2. And wouldn't you know it, you can just stick 0 into that thing. So always check to make sure at every step that if you can just do it. Because if you can just do it, you're done. And if it simplifies like it just did, because the natural log has that weird cool derivative, then that's it. Really one application of L'Hopital's rule. Just know that if it's a product or something, you're going to have to mess with it a bit to get it to where we can actually use the rule. So you have to make it look like a quotient first. And then I guess check to make sure that quotient is in fact an indeterminate form. So all that is to say, this just goes to 0 squared over 2. So that limit is just 0. And again, if you graphed it, I don't even think you'd need to look at a table. It's very obvious that it does go to the origin there. It's just that it's undefined at the origin. So we just figured out that, oh yeah, look, that actually is the limit.